All right, so in this video, we're going to be looking at math of finance formulas. We're going to start with the very, very basic simple interest problems, and we're going to work our way up to compounding and payments and continuous interest and all those other things. So let's begin with our simple interest formula. The basic interest formula is I equals PRT, where P is the principal, R is the rate per time period, and T is the number of time periods. From there, you can calculate the amount in the account or the amount that's due after a certain period of interest, which is just the principal plus the interest. And if you make your substitutions, you get that the amount is equal to the principal times 1 plus RT. Now let's go through and do an example. So if I want to calculate the simple interest charged on a credit card loan during a month when the average daily balance is $453.18 and the annual interest is 6% annually, that is a very good rate, then find the new balance. So the principal here is 453.18, R is 0.06, and the time period is 1 month. So since this is an annual rate, the time period will be 1 out of 12. And then we just multiply through and we get 227 to the nearest penny. When you're working with dollars and cents, it's generally, the practice to round everything to the nearest penny. And then the new balance, therefore, is going to be the old balance plus the interest. And so that'll be 455.45. Now, simple interest is one thing, compound interest is more common. And so when we look at the compound interest formula, we have the principal that still stands for the balance that you have at the beginning of the time period. R is the annual interest rate, N is the number of compounding periods per year, and then T is the number of years, so NT in the exponent. You will also sometimes see this formula expressed this way, where I is the interest per period, and M is the number of periods. So again, you'll see this in slightly different forms, but basically it is still the same thing. So let's walk through an example. So we want to save money for a down payment on a house in 2 years. If we set aside $10,000 into a CD earning 11% annual interest, that is also a very good rate. How much money will I have in my savings account for the down payment when the CD matures? Okay, so we know that it's compounded weekly, so N is 52. That's the number of compounding periods per year. We're saving for 2 years, so T is 2. Our interest rate is 0.11 since it's 11%, and our principal is 10,000. Again, I would be the interest per period, which would be the annual rate divided by 52, and M would be 52 times 2, which would be 104. And so when we put all of that together into our formula, this is what we get. And if you plug that into your calculator, then you're going to get $12,457.87. If you want to calculate the interest on this, how much interest was earned in that time period, you would take this balance and subtract the original principal in order to calculate the interest earned. Now, in this case, if I need $10,000 for a down payment on a new house in 5 years, so this is another example, but now we're working backwards from what we need. But I have only $8,500 to save right now. What annual interest will I need to get to save that much in the allotted time? So A is our future amount, that's our 10,000. So that goes on the left side of our equation. And then here, we only have $8,500, so that's our principal. So that's going to go outside the parentheses. R is what we are solving for in this case, and time is in 5 years. If we're compounding annually, then these two versions of the formula are identical. So we're going to divide both sides of the equation by 8,500 to get our 1 plus r to the fifth free. And then we're going to get 20 over 17. And then what we're going to have to do is take the fifth root to get rid of that exponent. And then we can subtract this value minus 1. And so what we find is that when you do that calculation, you end up with needing about 3.3% interest. Now, here's another example. We want to find out the time that we need. So suppose that I have $5,000 and I'm opening a CD to save money to buy a new car. I have $7,000 right now, or I have $5,000 right now, but the car that I can that I want needs $7,000. So the CD pays 8% interest compounded daily. I want to know how long will I have to save that money in order to get this car. So A is 7,000, that's our goal. P is 5,000, that's what we have. The interest rate that we're getting is 8%. And if it's compounded daily, then our denominator is 365 and our exponent is 365 times t. T will be the number of years. So we begin as we did with the last example. We start by dividing both sides by the 5,000. That gets us this expression. Now, in order to get to the exponent, because it's not a constant, we can't use the roots. Instead, we're going to use logs. So here we're going to take the natural log of both sides of our expression. That's going to get us to allow us to use this property of logs where we can bring the exponent outside the log and multiply out front. And now we have 365 and we have this log of 1 plus 0.08 over 365. Those are both constants. And so we can divide both of those out to the other side of the equation to divide log of 7 over 5. That will get t by itself. Again, 365 and the log both came over because they're all constant. And what that, when we solve that, plug that into our calculator, again, be careful about two things in the denominator when you put this in your calculator. Use an extra set of parentheses. What you end up with is t is about 4.206. So a little bit longer than 4 years in order to get the money. If you multiply this by 365, it's 1,536 days. Now, when you get to this number of days period, you have to round up because essentially if you round down, you won't have quite the money. So in a hypothetical problem, if this answer produced 15.01 cycles, then that would mean that 15 cycles isn't quite long enough to get that desired amount. And so you would have to go over to the next number of cycles in order to make sure that you met that threshold goal. Now, different compounding periods will show up in your problems. Annual would mean n is 1. Semi-annual would be 2. Quarterly would be a 4. Monthly is 12. Bi-monthly is 24. Bi-weekly is 26. Weekly is 52. And daily is 365. Obviously, other periods are possible, but they're less common. These are the ones that are most likely to show up. We've already seen an example with monthly and weekly and daily and annually. Now, aside from the compound interest formula, when we start compounding, our rates are going to effectively be a little bit higher because we're earning interest on the interest. So there is an effective rate formula that we can use to compare interests that have different rates and different compounding periods to see which one is going to be a little bit better. Generally, more compounding is going to be better, but depending on how different the interest rates are, the interest rate may still overcome any improvement in the number of compounding periods. So let's look at our example for effective rate. Suppose we are looking to invest some money in one of two banks. A Bank A, at Bank A, they are offering 7% compounded daily. At Bank B, they're offering 7.25% compounded annually. At which bank should you invest your money? So we're going to put them both into our effective rate formula and see what happens. So here in Bank A, we have the rate is 7%, compounding daily is 365. We're going to go through one yearly cycle. So that's 365 compounding events. And when you calculate this, you're going to end up with 7.250098%. And in Bank B, if you put in 7.25%, that's 0725 after the decimal. N is 1 because it's just one compounding period. And when you do that calculation, you get 0.0725 stop because you're only applying the interest rate one time. Essentially, what this is indicating is that the rates are actually virtually identical. The only difference is in the 1, 2, 3, 4, 5, 6, 7th decimal place, which would make Bank A very slightly better. But if you have a lot of money, you might make a couple extra pennies. But if you're just having, sort of hundreds or thousands of dollars, you may not even notice the difference in these two. If you keep your money in there a long time. If you keep it in there only a short period of time, I would go with Bank A just because you have to let it sit there for a year or you won't earn the interest on it at all. Now, when we start making payments on our compounding formulas, then they get a little bit more complicated. And so, again, our I is equivalent to R over N, where R is the annual rate and N is the number of compounding periods. And then we have these formulas. So the sort of broken out version, R is the payments, it's the repeated payments that we keep making. The formula here for annuities and loans has a negative exponent. And we have this R over N also in the denominator. Now, again, when you're dealing with these formulas, you have to be super careful about your parentheses because you're doing things in the denominator and in the numerator. I always remember this formula because there's another version of this formula for when you're adding to the balance, and that has a positive exponent. It looks otherwise very, very similar to this. The order in the numerator is flipped backwards, but basically they look very similar. But the negative exponent is part of what is indicating to us that the balance is actually coming down as we make payments on these accounts. The balance is being reduced. And so that's why, even though there is interest being applied that's making the balance go up, the payments are larger than the interest. And so the balance is actually decreasing over time. And that's how I remember this negative exponent. Negative exponents generally for sort of normal real world values are going to be smaller than positive exponents. So it's not the payments and the interest are kind of working against each other. So let's walk through an example of using this. Now, sometimes the annuities can appear in both of these contexts where you're adding to the balance or decreasing the balance. In both of the cases that this formula applies to, the balance is declining. So this would be where an annuity is paying out to the owner. So the balance is coming down because there are payments being made out. In the case of a loan, the person is paying to the bank to decrease the amount of balance that they owe on their loan. So let's look at an example. So suppose I wish to purchase a car that is sticker priced at $15,000. I can get a loan for 5% interest with the credit union. How much money will I have to pay each month if I take out a loan for 5 years? So I'm borrowing $15,000. That's my principal. R is equal to 0.05. That's my annual interest rate. N is equal to 12. That's my compounding cycle. T is equal to 5, that's 5 years. 12 times 5 is 60. And when I run this through my calculator, I divide this whole side of the equation right here times R is just a constant. So I divide my 15,000 by whatever this constant turns out to be. And again, take care when you're entering this into your calculator. You may want to calculate it in stages before doing the division. But it turns out to be $283.07. Again, round to the nearest penny. And if you make payments of $283 roughly, then you will be able to pay off the loan in 5 years. Now, the formula for the sinking funds and annuities is, again, the order of subtraction in the numerator is reversed and the exponent is positive, but they otherwise look very similar. These sinking funds and annuities are for when the balance is growing in the account. So either when you're paying into an annuity, so you're adding balance to the annuity that will eventually pay you back over time, in retirement, let's say, or if you're just adding a balance to a savings account. So you're saving money, but you're earning interest as you keep making these repeated payments. So again, maybe you're paying into a retirement fund, or you're saving up for maybe a down payment on a house and you can't afford the whole balance like we did in some of the previous compounding problems where you just deposit $10,000 into an account. Here, you want to accumulate up to a certain amount maybe, but you are not able to make the full payment, so you pay into it as you go. So this is a similar example. So they've determined that they are going to need $12,000 for the purchase of computers for their whole office 3 years from now. Their bank is willing to give them an annual interest rate of 4.5%. How large a monthly payment must the company make to the sinking fund so they have enough money for the purchase? So generally for these problems, we assume that the payment rate and the compounding period rate are the same, just to make lives easier. And so here our variables are the $12,000 we're trying to save up for, and the interest rate is 0.045. The number of time periods per year is 12. The number of years is 3, so 3 times 12 is 36. And we're looking for the repeated payment value. And so again, you may want to calculate this side of the equation. It's all of a constant except for the R, and then divide that into the 12,000, and you end up with $311.96. If they make that payment regularly into their savings account, then by the time they get to the end of 3 years, they will have the $12,000 they need. Now we're also going to look at continuous interest and the effective rate formula for continuous interest. Now, as the compounding period becomes more and more frequent, there actually is a limit to how much interest that you can earn. And some problems are just treated like they have continuous interest because there's no specific compounding period. Things like inflation or the stock market, they may fluctuate a little, but you can think of them as sort of a long-term continuous behavior. And so in those cases, we're going to look at the continuous compounding interest formula. Here, P is still the principal, R is still the rate per period, and if there was no compounding, and T is again the time, usually years. And then A is the amount in the account. So again, let's look at an example using this formula. And again, these problems will have to specify continuous compounding in order to use this formula. Suppose that you are investing $25,000 in an IRA account that is offering continuous compounding at 10% rate for 15 years. How much will be in the account? So our balance is $25,000. Our rate is 10%. and 15 years. And we just plug that into our calculator and we get about $112,042.23. Again, round to the nearest penny. We're keeping this money in the account a long time. So again, if we want to know the interest earned on these accounts, we would take this total, we would subtract the 25,000, and that would get us the interest earned. If you're trying to get into the time component, you would need to use the log and log properties as we saw in a previous example. Now, the effective rate for continuous compounding would be e to the r minus 1. And so again, we may compare interest rates. Now, if they're both continuous compounding, then the one with the higher interest is obviously going to be the higher, the better amount, because they're both compounding at the same rate. So normally you might be comparing, for instance, compounding monthly to continuous compounding. And then in the two comparisons, even though they will work basically the same way, you would be doing two different formulas to get the effective interest rate. But just to walk through the process, here, Bank A, the effective rate, we would have e to the 0.06 minus 1. So you can see is slightly, it's 6.1, 6.2% effectively. But when you put 6.2% into the continuous compounding formula, or to the compounding formula, compounding monthly, then we're using that other version of the formula we saw earlier. But this is still, even though it's only monthly and not continuously, the 2.2% difference in the interest rate is still big enough that compounding monthly is going to get you 6.37%, 6.38%. That's still higher than this. So even though the effective, the continuous compounding is faster compounding, monthly is enough with that even 0.2% difference that Bank B is still better.